Lightnings are fascinating. In this series, we will focus on the concept of electricity that you need to know to get the A star in IGCSE exams, starting with the topic of charges. Matter, as you know it, which makes up everything that you can observe in this universe, has several physical quantities like mass, density, momentum, energy, and so on. One of those quantities are charges, and charges are responsible for some of the cool effects you can observe in nature. For example, if you look at this video, you will see a Van de Graaff generator, which is a device used to generate charges. As those charges distribute themselves on the surface of those kids, they start to spike their hairs as shown. So to understand charges, we need to deeply understand matter. And we know matter is made up from particles which oscillate and vibrate in all directions. The basic component of particles are atoms, and atoms are made up from protons and neutrons along with revolving electrons around them. Those are the three building blocks of atoms. Protons have what we call as positive charge, while electrons have negative charge. Neutrons have no charge, so we'll just disregard them from this discussion. And the thing about charges is that they exert attraction and repulsion forces on each other. Opposite charges attract, so protons and electrons would attract each other, they would exert forces on each other, as shown. This effect is due to the property that protons and electrons have, which is the property of charge that causes them to attract. This is how they are in nature. However, like charges will repel. So if we place two electrons next to each other or two protons, then they would repel as shown. So that's the meaning of charges. It's just the property of matter that causes electrical forces. Those forces could either be attraction or repulsion. Note that the naming of the charges, positive and negative, is just arbitrary, what scientists chose to call them. They could have been called charge A and charge B, or charge 1 and charge 2, but the standard selected is positive and negative because they are different. Alright, now let's look at how those charges act in an atom. Well, you have equal number of protons and electrons in an atom. So you have 4 protons and 4 electrons in this example. Therefore, we can say the atom is electrically neutral, which means there is no net charge. Every proton attracts one electron and the other way around, so they kind of balance each other. And there is no net charge of the atom. So what does this mean? If we have two neutral atoms next to each other, then each one of them have an overall charge of 0. Therefore, no electrical forces are generated between those atoms. You can think about them as being two neutrons next to each other. They don't generate any forces, simply because each atom by itself is considered neutral. Within the atom there are those forces, the attractions between the electrons and protons, but the overall atom has a charge of 0, and that's why atoms in their neutral state are considered stable. They don't exert electrical forces on adjacent atoms. Atoms are electrically neutral by default. However, they can become positive ions if they lose an electron or more than one electron. For example, look at this demonstration. If one electron jumps out from the atom, then if you look inside the atom, you will see that you still have 4 protons but only 3 electrons. And this results to an overall charge of the atom, which would be positive 1 charge. The positive means that we have more protons, and 1 indicates the difference between them. Similarly, the atom can become a negative ion if it gains electrons. such as shown. If one electron entered the atom, now in this case we have 4 protons, they didn't change, but we have 5 electrons. So when we look at the overall charge, we will find it to be -1, which indicates there is an excess of negative charges. So in general, a neutral atom can be represented as shown, either with equal positive and negative signs, or simply nothing. While a positive ion can be represented as shown, and a negative ion can be represented with a negative sign. So when we look closely at matter, it's made up from neutral atoms. Since there are millions and millions of those atoms, we don't keep on drawing the charges of each one of them. We simply draw a representative sample as shown. If the matter has more positive charges than negative, then we can say it has an overall positive charge and can be represented in this way. Similarly, if it has more negative charges than positives, then we can say this object is negatively charged and can be represented in this way. You can tell in the positively charged outfit there is a surplus of 2 positive charges, while in the negatively charged outfit there is a surplus of a negative charge. Now the number of positives and negatives indicates the amount of charge. So definitely more positives means it's more positively charged, or the other way around. So thinking about what we learned so far, let's reflect on the first example we saw. Since we know like charges repelled, which means when the students were touching the Van de Graaff generator, charges traveled through them and their hair is considered to be positively charged or could be negatively charged. That's why the hair tries to repel away from the adjacent hair. And that's the meaning of charges. It's something that is accompanied with matter. Matter exists, then it has this property. And we only have 2 types of charges. We classified them based on the forces they exert. Unlike charges attract, while like charges repel. So let's look at the second topic, which is charging. How can we charge an object, which means creating an imbalance in the amount of charges? Let's say we have those 2 objects, a balloon and a winter glove. They are made up from particles, which are neutral by default, as shown. If you rub the glove on the balloon, well, this rubbing effect is going to create a transfer of negative charges from one material to the other. We can then remove the neutral particles from both objects and we can see that the balloon has a surplus of positive 3 charges while the winter glove has a surplus of negative 3 charges. This is called as charging by friction. The friction between those 2 materials that occurred during rubbing caused some electrons to transfer from one object to another. And this happens because one of those materials have more tendency to accept electrons than the other. In this case, the winter glove has more tendency to accept electrons. So for example, if we change the balloon with a plastic pipe and we do the same rubbing, then this time the electrons will transfer from the winter glove to the plastic pipe. So this time the glove becomes positively charged while the plastic pipe becomes negatively charged. Comparing that to the balloon, we can see that the PVC pipe has more tendency to take the electrons than wool. That's why electrons travel from the wool to the pipe, while the wool has more tendency to take electrons than the balloon. From this information, we can conclude that the PVC pipe has more tendency to take electrons than the balloon. It's very important to note in those examples we demonstrated, only electrons are the charges that are able to move in solids. And this is because they are lighter, they have much lower mass and can exit the atom, unlike the protons which are held deep in the atom within the nucleus at the center of it. So to generate a positive charge, you need to remove electrons. Another important note is that charging by friction only happens for insulating materials. So let's see what that means in the coming section of insulators and conductors. Insulators are made up from materials that are held together by covalent bonds, strong bonds. So for example, the woolen glove and the balloon, even though the friction forced some of the electrons to transfer from the balloon to the glove, as the electrons reach the glove, they can't really transfer within the glove. The bonds within the atoms prevent any further transfer of electrons. You can say those negative charges are stuck at that side of the glove. Materials that trap charges and do not allow them to flow are called as insulators. And that's why you can charge an insulator, because whatever charge you give them, they are trapped inside. It's not easy to get rid of them. Conductors, on the other hand, such as this metal rod, are bonded together by metallic bonds, which means there is only one or few electrons in the outer shell, and they can easily leave the atom and transfer from one atom to another as shown. Metals have free moving electrons. So even if you charge it and you added 3 electrons, for example, by whatever means, as you can see over here, well, whenever this happens, electrons keep on repelling each other, and they will do that until they reach the other end and transfer to the hand, as shown. So basically, you can't really charge a conductor, because whatever charge you give it, due to the electron's ability to transfer between the atoms, when the charges reach one end, they will just exit from the other end. That's because they allow them to flow. So we looked at insulators and conductors. So let's look at insulated conductors. Now an insulated conductor is something like this, which has a conductor component mounted on an insulator, in this case the metal and the plastic holder. If we try to charge it, let's say by using this cat over here and the eraser, applying some friction, the cat and the eraser will be charged with opposite charges. They are both insulators. And by the way, cat's fur is a good charging material. If we take this eraser, placing it close to the conductor, those electrons can travel through the conductor, or at least some of them can. And when this happens, although the electron will be repelled to the other end, however, the other end is connected to an insulator, which can prevent any further transfer of charges. In the previous example, the metal rod was connected to the hand, and the human body can be considered as relatively conductive. That's why the charges were able to transfer from the Van de Graaff generator to the hair in the example I showed you earlier. Insulators and conductors and insulated conductors are used a lot in our daily lives. For example, in the electrical wires, they are usually made up from conducting materials wrapped by insulators. So by now, you have the idea about insulators and conductors. Now let's look at grounding and see what does that mean. And to do that, we first need to look at how do sparks form and what is the meaning of static electricity. Let's look at this example. If you have a carpet as shown, which is initially electrically neutral. Now when the person on the left starts walking, as he walks, his foot will keep on rubbing the carpet. As he does, he will be charged, and in this example he's negatively charged, while the carpet will become positively charged. When the other person reaches out for a handshake, since there is a great imbalance of charge on the boy to the left, those charges will try to repel each other to the point where they are going to escape the first boy and jump to the other boy as shown. That's when the spark is generated, when the electrons travel through air. Air is actually the one that generates those sparks, but it was forced to by the moving electrons. This type of electricity, we call it as static electricity. The electricity that is not moving, that is stored in objects. And for those charges to be released, they have to be discharged whenever they get the chance to, such as the handshake over here. So the definition of static electricity is basically the imbalance of electric charges within or on the surface of a material. Those charges will remain until they are able to move away by means of electric discharge, as in this example, or what we will study later, electric current. Now let's look at a real life example. What you see over here is a person petting the cat, which generates static electricity. When a lot of charges build up, the static electricity starts to travel to the nearby radiator as shown, as the radiator is a conducting material that can collect those charges and pass them on. So what does grounding have to do with all of this? Well, grounding is actually the process of connecting an object to the ground or to the earth with a conducting material to remove any imbalance of charges. So for instance, if the charged boy to the left held a piece of conducting material and this conducting material was connected to the ground, then the charges can travel through the conducting material to the ground as shown. So grounding basically means providing a path for the buildup of charge for static electricity to pass to the ground. So for instance, if we have this case with an insulated conductor, in this example the scissors, which is negatively charged, if you connect that part to the ground, then those negative charges will transfer to the ground. While if you have another insulated conductor that is positively charged and you connect it to the ground, then those positive charges will attract negative charges to balance out from the ground as shown. You can always assume the Earth as neutral, with the ability to neutralize any object conducted to it, either by taking or giving electrons. So if you connect a positively charged object to the Earth, then this positively charged object will take electrons so that it balances out, while if you connect a negatively charged, then those negative charges will keep on repelling each other until they reach the Earth. This is grounding, or sometimes called earthing. Let's look at some practical examples. Usually, people who work with electronics can't afford to become charged, because if they become charged and they place their hands close to those electronics, the charges can transfer from them to the electronics, which could damage them. Therefore, those types of workers wear a static bracelet. They wear it around their hands as shown, and then the other end is connected to a metal rod that is connected to the ground. Basically, they are grounded so that any buildup of charge that can occur in them from walking or any type of motion, then those excess charges can travel to the ground instead of traveling to the electronics and damaging them. Let's look at a more serious example, which happens when you fuel a car. So if you look closely over here, when you attempt to fuel the car, well, the petrol or the fuel is going to transfer through the pipes to the tank. As it does, there is some friction between the fuel and the pipe material. This will generate a charging effect. The pipe could be negatively charged and the fuel becomes positively charged, or the other way around, doesn't matter. When this happens, there would be a great imbalance to the point where some of the charges will transfer back to the fuel as shown. As they do, they can generate a spark, ignite the fuel, and start an explosion. So in order to avoid that, you must ground the fueling pipe, which is actually the case. It is connected by a conducting material to a piece of metal that is deeply inserted to the earth. You can see it over here. That's also the case when you fuel tankers. As you can see, this end is connected to the ground whenever fueling happens. Also, if you have fuel stored in containers, well, you have to connect it to the ground, just in case. We don't want them to be charged at all. One more thing you need to know, instead of drawing the earth every time, we can simply use this symbol. That's the grounding symbol used in electricity, so remember it. This is another example shown that happens when fueling the plane, where the tanker and the plane are both grounded. So that's grounding. Now let's look at a different concept, which is induction. If we take an insulated conductor that is initially neutral as shown, and then place a positively charged rod next to it, Well, since in the conductor part, electrons are free to move, they will be attracted by the positively charged rod as shown. We can then remove the balanced out charges and we will notice that one half of the conducting sphere is negatively charged while the other half can be considered to be positively charged. Similarly, if we placed another neutral sphere, but this time we use the negatively charged rod, then the electrons in the sphere will try to repel away from each other as shown. If we eliminate the balanced charges at the center, then this is what we would get. One side is positively charged while the other side is negatively charged. Note that if we remove the charged rods, the spheres will become neutral again as the electrons will flow towards the positive charges one more time. So that was induction. Now let's look at how can we charge by induction. Well, if we connect the conducting part of the insulated conductor to the ground, then we give a chance to those positive charges to neutralize from the ground, as shown. Note that the negative charges on top will not be neutralized because they are still attracted to the positively charged rod. So now, if we unground, we basically trapped those negative charges in the conducting material as they have no way to neutralize currently. If we then remove the rod, well, those negative charges will try to repel away from each other as much as possible, and they will distribute evenly around the sphere as shown. Similarly, in the other case, if we ground it, this time the negative charges from the sphere will transfer to the ground as shown. So when we unground, we basically trap the positive charges. If we then remove the rods, the positive charges will also distribute evenly around the sphere. However, this time, other neutral atoms in the sphere will transfer their electrons around them. In this manner, so those positive charges will neutralize and we can just hide them and positive charges equally distributed. This is because positive charges cannot really move. It's the electrons that can move inside conductors. So make sure you remember the steps of charging by induction. The first step is placing a charged rod near the insulated conductor. This will cause induction. Then grounding the conducting part. This will discharge the repelled charges by the rod to the ground. Then we unground. This will prevent any further discharge to the ground. Finally, we remove the charged rod away. This will cause equal distribution of the charge on the outer surface of the conducting part. Make sure you avoid removing the rod before the grounding or the ungrounding step, as this will neutralize the insulated conductor, therefore no charging will occur. Think about it. So that was induction and charging by induction. The final thing for today is polarized insulators. There is just a slight difference between polarization and induction, so pay attention. We've seen induction so far, but induction happens in insulated conductors. Let's say we take an insulator, such as this plastic liquid container, which has atoms in random distribution and orientation as shown. If we placed a charged rod nearby, well, this time, since it's an insulator, electrons cannot travel freely. However, the atom itself can orient itself in the following pattern. It is still electrically neutral. But if we highlight the middle of the plastic bottle, we can say that the number of positives and negatives balances out. This part is neutralized as for each positive there is a negative charge, as shown. So let's eliminate them from the drawing, and we will notice that one side is negatively charged while the further end is considered as positively charged. This effect is called as polarization. It's slightly different than induction, as in induction electrons do transfer, but in polarization electrons do not transfer. It's just that the orientation of the atoms generate separated charges on each end. Polarization happens for insulators, induction happens in insulated conductors. So the last thing you need to know is that neutral objects can be attracted to charged objects. This is due to either induction or polarization. For example, if we look at those paper pieces with a negatively charged balloon close by, this balloon will cause those small pieces to become polarized as shown. Because of this, the positive charges are attracted towards the negatively charged balloon, while the negative side of the paper is repelled by them. However, this time, since the positive charges are closer to the balloon, therefore the attraction force is more than the repulsion force. It's just a matter of distance. The positive charges are closer, therefore more force. This will cause an attraction as shown. And that was the end of this lesson. Thank you for watching. Stay tuned, there is still a lot to learn in this chapter. Don't forget to support by subscribing and liking and sharing with your friends in order to continue receiving similar content. See you in the coming video.